Okay, very good. Thank you for mentioning that, Russ.
Sure.
So sorry again for that. So you see here, that's the geometry. So you've got the tower here, which is indeed a fixed geometry. It doesn't move. Meanwhile, the blade geometry will be rotating on their axis. Okay, so just to show you the way we would proceed in that setup would be the following way. As usual, we go from left to right and we fill up just the different options. So first with the engine, which is here a 3D simulation, we work with a single phase analysis, and it's an external simulation since we'll have a wind tunnel to blow wind on that wind turbine. Okay, so problem is isothermal as well, and no problem on that. Now, let's set up our wind tunnel because you can see the dimensions of that geometry are pretty large. We've got about 45 meters, not on diameter, but almost, and the tower is about 81 meter of height. So it's pretty large. My initial wind tunnel is too small, so I'm gonna change my size of wind tunnel. So you can see I can just input, for example, 500 by 200 by 200, like that. Very good. So we've got our wind tunnel set with the correct dimensions. I'll just move, well, the different the position of the wind tunnel so that we can get something that is a bit better. That means turbine a bit upward, and I'm just gonna move the ground so that it can, you see, cross the leg and doesn't have any gap in between the leg and the ground. Okay, so my ground is still not enabled, but again, just switch it on. So ground wall, I can just enable it. And then you can see, for example, we've got 0 velocity applied at the moment. So here is when the new interface can be very handy. You can see we've got now a new function editor. So it's a window that opens and you can actually write down your loads. And you can see if I, for example, try to set up any sort of flow, for example, sinus, you see it proposes me different functions. And when I select a recognized function, it also highlights them with colors. So that's a new low editor that we did not have in the previous editions of XFlow, but now it's available. So it's pretty useful. In that case, I'm gonna use what we call a power law. Okay, that's typical. I won't impose a profile of constant velocity, but instead I want to show you how to apply a law that will depend on the height. That means at higher altitudes the wind blows faster, but close to the ground the value of wind will be lower. Okay, sort of wind of boundary layer profile, but on large scales. Okay, so for example, that's a law where we will define our height according to the middle of our turbine, which is in this case aligned with y equal to 75. So that's why I put if y 75. And then I will just divide by a scaling factor and use my power law with 143 as a power law. So that's a typical power law profile that you can use for this kind of application. So if you see, that law is depending on y. So I can see now that my profile will provide me, well, not a straight line, but something that is sort of well, logarithmic profile, right? And so this is what we get, and this is what we use, so that we got different values of velocities at different positions in y direction. So you see that 100 meters we provide 12 meters second, meanwhile at 300 meters height we'll have 30 meter, and so on. So I'm just happy with my law and just can accept, and this law is then input here by XFlow. Now let's move, because I've got a short time for the demo, and so this is where you get really the interesting part. It's how do we define that wind turbine? You've seen we can define it as enforced motion. That means I could switch it to an enforced motion and set myself the law of rotation. For example, I wanted to have a quarter of rotation every second. and then I would have a, for example, minus 90 degrees times t. That means in 1 second of time it does 90 degrees. So you can see now we have the following low, oops, sorry, I applied that to the tower instead of the blades. So that's why you can see my tower is now rotating, and that's not consistent at all. So sorry for that mistake. What I can show you now is how it happens when I do things right. And rotating the blades on x-axis with 90 times t, minus 90 times t low. So you see it's very easy for you to actually see your mistakes in XFlow and defining the motion, so you can just realize that you've defined the wrong input just watching on the timeline the position of the blades. Okay, and then we just have to set up the simulation time and this kind of parameters. So let's say we'll do three rotations, so 12 seconds, since we've got a 1 revolution in 4 seconds. And now we can define, for example, well, a resolve scale. So first I want to use my adaptive refinement in that case, because I want to refine near my blades, near my geometries, but also with the wake refining on the far field as it develops. So I'll use 8 meters on resolve scale because my domain is pretty large. I've got 500 meters in X and 200 meters in the other direction, so I need something much larger for the resolve scale. And then I'll try to use something finer for my blades, as well as my tower, as well as my wake resolution. As you can see, I've got 10 meters, 0.5, 0.5 for tower and blade, and wake resolution to 0.5 as well. I could adjust my frame frequency to have something that's not too high frequency here. And finally, I'm ready to run. I could just add a few probes if I like to measure anything in the flow field, such as, well, I don't know, the pressure, velocity at some point of the domain during the simulation, and monitor those points. I could just run that. So I just have to save this test, and now can just start the computation. And you can see the way it does is it tells you a lot of different messages, logs, okay, which are the domain generator first. I've got 270 elements in that simulation. It all initialized correctly, and then it starts iterating. So I've got my frame number 0 computed, which is the initial frame, and you can see then a few time step occurs, and then frame 1, and then frame 2, and so on. So simulation will just runs, and you see the bar will just fills as it computes and as the frames are being computed. So just in the meantime, my calculation is starting. I can actually do my post-processing at the same time. So there is no problem with that. I can create, for instance, a cutting plane. And one of the new things with the new XFlow is that you don't have this ray tracing technology anymore, but you also can create a plane and rotate your camera, and you don't have to refresh the plane again. That's one of the new things. We just changed completely the rendering of the solutions as well as for the geometries, and it's much more convenient in that aspect. I can also check on my domain structure, see how it looks like, and one thing also you can see on that new version again is really the good way of watching the lattice structure. You can see here previously we had some sort of crosses and marks to define the different borders between levels. Now it's a proper let's say Cartesian mesh that is being plotted, and you can really realize how fine, of course, is your lattice structure very conveniently. You can also color it by level so that you can appreciate the different lattice structures and see different options like the normals and the broken links, which is basically the points on the surface detected by this lattice. Okay, so you've got a lot of different new options with that version, which are pretty cool. And that's are offered by XFlow. Okay, but more interesting, you see my simulation starts rotating, my blade starts rotating. In the meantime, I can also, for example, monitor, well, different factors, such as, for example, my moments in x-axis, which could be a good indicator of the convergence of the forces over my blade. And you can see as the computation occurs, we've got the lines are being plotted and constructed. So it's something you can monitor during your simulation perfectly with no type of problem. And yeah, I think I'll just finish by showing you very briefly the results of the simulation when it's done, because I don't want you to wait for the simulation to end by this webinar. We're already short in time, so I've got here the final solution run, and you can see these data of the blade, for example. So MX, you can see the MX is converging towards some values around minus 110 Newton meter maybe, and the different forces on the blade acting on the blade as well. You can see on the flow field that the wake has been developed. You've got the domain structures that is showing the refinement that is adaptive and following, tracking it down all these eddies due to bivorticity. And we can of course watch as well, for example, the vorticity field showing actually this helicoidal shape induced by the rotations of the blade in that case. So let me switch off the interpolation. Okay, and you can see here that rotating shape of the blade. And very briefly to end with this, if I'm allowed to do that, I will just show the difference with a simulation where the blades have been defined as a rigid body dynamics. So you can see here blades in that simulation are defined as a rigid body dynamics behavior. And instead what we do is we impose a certain mass properties with inertia tensor and then different degrees of freedom. So we say it's fixed in translation, but it's allowed to rotate around X rotation axis. And finally, you could define some external forces or moments that we don't do in that case. And when you look at this, it allows you to see, for example, the rotational speeds as a function of time, which starts being 0 at the beginning and, lowers until it finds an equilibrium to a certain position. This is where, when your wind turbine actually is converged for these wind conditions and determines the rotational speed achieved by the wind turbine on those conditions. Also looking at the moment in the direction shows you a resistance moment that is higher at the very beginning, but as soon as the rotational speed is established, then the moment is close to 0, obviously, because of the wind turbine is already rotating with inertial effect itself, and so only very little moment is required to make this rotate. Okay, I think I'm done, so thank you everyone for listening. Maybe we can have 5 minutes of questions and answers.